we're going to talk about how the action potential is propagated from the axon hillock to the axon terminal. And we're going to talk about propagation in myelinated versus unmyelinated axons. So an action potential, so this is what we were kind of just describing here. An action potential occurs at a given spot along the neuron. And so we've got a voltage change, we've got the membrane potential change at this specific spot, for example. And so it's really kind of ripping down the length of the axon from the axon hillock where it's really initiated all the way down to the axon terminal as we've been speaking about. And so what's really happening if we look a little bit closer is the kind of contagious nature where the current is being spread because this segment of the neuron is depolarized. And so it's going to influence this adjacent segment to become depolarized. But when the second adjacent segment is depolarized, the previous segment is now in its refractory period. It's still in its repolarization period. And so the action potential cannot move backwards to this segment. It can only affect or, impact the adjacent segment again, which is the following segment. And so the action potential can only move down the length of the neuron. Okay, I hope that makes sense. And so after this segment is now in its relative refractory period, then we see the following segment become depolarized, and the initial segment is now in its resting state again, and then we can fire another action potential. And so action potentials go down the entire length of the neuron. They are just jumping from segment to segment. They are actually very slow in unmyelinated neurons. So this is kind of looking at what happens in unmyelinated neurons. And so if we think about myelination, myelination is the wrapping of neurons in these myelin sheaths that helps to speed up conduction. In unmyelinated neurons, we don't see this. Why? Because action potentials are moving from segment to segment to segment, kind of the local stops on a train. If you think about a train moving and it's going local, it's going stop to stop to stop to stop. And so it goes very slow. Because there's no myelin, the amplitude of each section is going to be the same without really changing or decreasing the value of the action potential. It's going to be moving from spot to spot to spot. So again, we've got site A being depolarized. That kind of infects site B. Site B is now depolarized. And so the action potential moves forward to site C. Site A can no longer be repolarized, so it cannot move backward. And so it keeps moving from segment to segment. So this is just kind of reiterating that here. We can see the exact membrane potential value. So we know it's negative on the inside of the cell, positive on the outside. And we know that site A is in rest, site B is in rest, site A is depolarized. That kind of moves along, right? Site B now becomes depolarized. Site A is back in its refractory state. Site C is now going to get infected or depolarized, if you will, and site B is now in its refractory period. And that happens again and again and again from each segment of the neuron. In myelinated neurons, this is a little bit more rapid. This is a lot more rapid, actually. And think about this as a train that's moving express, right? It's just skipping a bunch of stops. It's going to the main stops, and it's kind of just jumping along the myelination segments of the neuron. So this is the purpose of myelin. It's a fatty layer that wraps around the neuron, and it's kind of like the conduction of a cable. It simply speeds up the velocity of conduction. And we've got these spots in between these myelinated segments where there's no myelin. We call these nodes of Ranvier. And this is where the action potential is actually happening. So this is a node of Ranvier here. It's absent of myelin. Here's a second node of Ranvier, also absent of myelin. And so we've got sodium moving only at these spots, but the action potential kind of just jumping from one node to the other and leaping down huge segments at a time. And so it can move very fast down the length of a neuron. This is why heavily myelinated neurons have a much faster velocity. These are usually neurons that travel for longer periods of time. So think about really long nerves like the sciatic nerve, which is the longest nerve in the body. It is heavily myelinated, and that is so it can have extremely fast rates of conduction down the length of that neuron. We call this style of conduction saltatory conduction. So essentially, saltatory conduction is the jumping of the action potential from these nodes of Ranvier to the subsequent nodes of Ranvier without actually touching each specific segment of the neuron, okay? So again, you can think about it as an unmyelinated neuron being a train taking all the local stops, and a myelinated neuron being a train just taking express stops and moving much faster. You can tell I lived in New York, I'm sure, at this point. Okay. So let's see this kind of in action here. So we've got a myelinated neuron, and we can see that myelin sheath, the way it's kind of, separated in chunks. And we've got the depolarizing event moving down in kind of gaps, kind of leaping in between those spots. We can see here that the spot that has myelin doesn't actually change, right? Inside the cell remains negative. So the action potential doesn't actually touch each segment of the neuron. It's really leaping from these interval spots down the length of the neuron. And as you would imagine, this type of conduction helps to speed up the movement of the action potential. So let's talk about the speed of the action potential. So it's going to be increased by things like an increased diameter, which helps to reduce the resistance. So if you've got a larger diameter of a neuron, it's less resistance to prevent dissipation of that current moving down the length of the neuron. Also, if we have myelination, we will increase the speed for reasons that we just explained. So we can think about some examples here as far as the variation of diameter and the variation of conduction velocity. So we can think about small, tiny fibers, for example, our autonomic fibers, smooth muscle fibers, cardiac muscle fibers, really small in diameter, really slow as far as their conduction velocity. And then we can compare that to thicker neurons, much thicker in diameter, such as, again, the sciatic nerve is a really good example, that are innervating sensory organs or maybe muscle. So for example, large bulk of muscle like the quadriceps muscle and so on, they're gonna have thicker neurons, they're gonna have faster conduction velocities. Okay, so we can compare both ends of the spectrum, and we can look at some different fiber types that would be examples of these different diameters and these different conduction velocities. And if you really think about it, the autonomic nervous system doesn't need the quick responsiveness that the sensory system does, right? Think about you running from a threat, a bear or a lion. You need to perceive that immediately. You need to be able to see and hear and feel and touch and smell things quicker than you need your autonomic system to work. Your autonomic nervous system, first of all, it's on autopilot, so you don't have to consciously think about it. And so we can see that disparity in the conduction velocity of our sensory system, which needs to happen immediately, versus our autonomic nervous system, which doesn't have to be as responsive. Alrighty.